Hi everyone, welcome to our first lecture on induction motors. Induction machines in general are very similar to synchronous machines. Both are three-phase and AC. However, unlike synchronous machines where generators are a lot more common than motors, for induction machines, motors are a lot more common than generators. Majority of industrial applications for three-phase motors are in fact of induction motor type. The next few lectures, we're going to focus on induction motors, and then we'll shift our attention to induction generators, where the machine is trying to produce electricity. Before we get started with our discussion of induction motors, let's revisit synchronous motors first. If you recall from our previous discussion, synchronous motors are not self-starters. What does that mean? If you plug in a synchronous motor into the supply, without external help, it's not going to be able to run. It needs some sort of an external circuit that can provide a starting torque for it. Last time we talked about a few options, and if you recall, one of them was the damper windings. Now these damper windings are metal bars that you place in the face of the rotor poles, and they are short-circuited on both ends, forming some sort of a cage structure. When you place the damper windings in the presence of a rotating magnetic field, which in this diagram I'm showing with B of S, a voltage is going to be induced in them. Since the bars are short-circuited on both ends, a current is going to flow as a result, creating a torque of its own, which in this diagram I'm showing as B of W. Now the interaction between B of S and B of W is going to create a torque for me, which in this case becomes unidirectional and will help the motor start running and get close to synchronous speed. For a synchronous motor, the operation of damper windings is temporary, only during startup. Initially, the field winding is disconnected. Damper windings will generate a unidirectional torque that will help speed up the rotor close to synchronous speed. As we get close to synchronous speed, we will connect the rotor field winding and the motor will lock into synchronous speed. However, if you think about damper windings as an individual entity, you will see that they have a lot of benefits for us. First and foremost, they provide mechanical torque for us, which is what we expect to see in a motor. Second, and perhaps more importantly, they do this without a need for an external voltage source. Remember that a synchronous motor requires an external voltage source that will generate the rotor's magnetic field. In addition to that, this connection, if you recall, is made possible through slip rings and brushes, which would generate additional losses and wear and tear. Since you don't have that external source, you're not going to have the brushes and slip rings anyway. So no wear and tear and no maintenance. In fact, damper windings are so efficient that they can operate on their own. They can create a motor operation for us. They create a torque, they don't need an external source, they don't need any additional maintenance. This creates the essence of the second class of motors, induction motors. Now in terms of the structure, an induction motor is very similar to a synchronous motor. The stator has basically the same structure. Both machines are three-phase, both machines have distributed windings. So when they are connected to the supply, both machines are going to create a rotating magnetic field. What differs between the two is the rotor structure. As opposed to the synchronous motor, in which the rotor has a field winding connected to a supply, in induction motors, rotor could be either wound rotor or cage rotor. Wound rotor consists of a series of windings, three-phase windings that is, which are short-circuited together. And the cage rotor is essentially the damper winding that we just talked about. Metal bars that are placed into the face of the rotor poles and are short-circuited on both ends. Now, how would such a machine operate? As I mentioned earlier, today's focus is on induction motors, so we will only focus on motoring mode of operation. In a few weeks' time, we will shift our focus to induction generators and we will see how this machine can generate electricity for us. But today we'll talk about a sequence of events where you have a three-phase induction motor and you plug it into the three-phase supply. As you do that, three-phase balanced currents are going to start flowing into the stator windings. This, as we saw before, is going to create a rotating magnetic field that will rotate with constant speed and constant magnitude. In this diagram, I'm showing this rotating magnetic field with B of S, S for stator, and the speed with N of S. I'm choosing N because this speed is in RPM, as opposed to omega S, which is in radian per second. But the concept is the same. Now, B of S is going to be rotating in the periphery of the stator. As it does that, it crosses the rotor bars. And as we have seen before, if you place the conductor into the rotating magnetic field or a moving magnetic field, a voltage is going to be induced in it. This voltage is going to depend on the relative speed between the conductor and the magnetic field, the magnitude of the magnetic field, B of S, and the length of the conductor. So the voltages are going to be induced in different metal bars. Since these bars are short-circuited on both ends, a current is going to flow as a result. And once you have current flowing in a conductor, it's going to create a magnetic field of its own. We will call that B of R, R for rotor. Now the interaction of the original magnetic field, B of S, and the resultant magnetic field, B of R, is going to generate a mechanical torque for me. This mechanical torque is going to be the cross product of B of R and B of S, and is what creates motion for my motor. Let's do activity 1. Can the induction machine rotate at synchronous speed? At this point, I'd like to ask you to pause the video and think about this question. Once you're ready to proceed, hit play and we'll discuss the solution. Now, for an induction machine to be able to rotate, there must be some sort of mechanical torque applied to the rotor. As we saw in the previous slide, this mechanical torque is generated because of the interaction between the rotating magnetic field of the stator and the magnetic field of the rotor. The magnetic field of the rotor is generated because of the currents that flow in the rotor structure, and these currents are the result of the voltage induced in the rotor bars. Why are these voltages induced? Because we placed a metal bar in the presence of a rotating magnetic field. In other words, there was relative motion between the magnetic field and the metal bars. If the machine rotates at synchronous speed, both the metal bars and the rotating magnetic field are going to be rotating at omega S, synchronous speed. Hence, there will be no relative motion. As a result, no voltage will be induced, no current will flow in the rotor structure, and we will not have a magnetic field for the rotor. If B of R is 0, mechanical torque will be 0. With no torque applied to the rotor is going to slow down. So the rotor can never run at synchronous speed, because if it does, no torque is going to be generated and the rotor is bound to slow down. From the previous discussion, it's obvious that the motor cannot get to synchronous speed. It can run from 0 to very close to synchronous speed, but it can never get to synchronous speed. We have to have a metric by which we can indicate what the speed of the motor is. And that metric is the rotor slip. Rotor slip indicates the difference between the synchronous speed and the mechanical speed. Now, if you remember, for a machine with P number of poles that is connected to a supply with frequency f of E, which in our case is typically 60 Hz, the magnetic field of the stator rotates at a synchronous speed which is 120 times f of E divided by P. The rotor is going to turn at a different speed. We call this the mechanical speed, and we show it as N of M. Now obviously there will be a difference between the two. The difference between N of S and N of M, normalized based on N of S, is called the slip of the motor. So S equals n of S minus n of m divided by n of s. And if you work with this equation, you can find the mechanical speed. Mechanical speed, n of m, is 1 minus s times n of s. S is a positive number, but is typically very small, which based on this equation, it tells you that the motor can never run at synchronous speed, but it can get very close to it. So an induction motor will always run below synchronous speed. N of m is always going to be less than n of s. Let's move on to activity 2. Here I'm posing 4 very important questions related to operation of induction machines. Similar to before, I'd like to ask you to pause the video at this point, think about these questions. Once you're ready, hit play, and you will see the answers. Question number 1. What is the slip for a synchronous machine? The slip is n of s minus n of m divided by n of s. For a synchronous machine, the mechanical speed is a synchronous speed because the machine is locked to the supply's frequency. So the slip becomes 0. Question number 2. What is the slip for a rotor at standstill? At standstill, the rotor is not going to be moving. So n of m is 0. Hence, slip becomes n of s minus 0 divided by n of s, which is 1. Notice the range of speed for an induction motor varies from 0 all the way to very close to synchronous speed. Similarly, the slip changes from 1 all the way to very close to 0. Question number 3. What is the relative speed of the rotor with respect to B of S? Now, B of S is the rotating magnetic field of the stator, and it rotates at a speed n of s. The rotor, on the other hand, rotates at n of m. The difference between the two is s times n of s. We call this the slip speed. This is the relative speed between the rotor and the rotating magnetic field of the stator. And the last question, what is the relative speed of BR with respect to BS? This one is a bit tricky, and you're going to have to picture how the motor operates. The rotating magnetic field is going to be rotating at speed n of s. However, this is the speed that an external observer who is stationary sees. The rotor itself is not going to be stationary. The rotor is going to be running at n of m. So from the point of view of metal bars and the rotor structure, this rotating magnetic field B of s is not running at n of s, is running at n of s minus n of m, which is the relative speed between the two. Now this is going to create or induce currents in the rotor structure, and these currents, which are three-phase, are going to generate a rotating magnetic field of their own, which is the rotor's magnetic field. This magnetic field is going to be rotating with n of s minus n of m. Why? Because it's the relative speed between the two. However, the rotating magnetic field is itself mounted on the rotor structure, which is running at n of m. So BR, in fact, is running at n of s minus n of m plus n of m, which is n of s. Now, BR is running at the speed n of s, which is the synchronous speed. B of s is running at synchronous speed as well. So the relative speed between the two is going to be 0. Another important parameter associated with induction motors is the rotor frequency. This might sound a bit strange to you. You would expect that if you connect a motor to 60 Hz, everywhere in the motor all voltages and currents are going to be 60 Hz. Well, in practice, this is not the case in an induction motor. Why not? The reason kind of comes from the last part of the previous activity. Notice that if you have a stationary winding, which is exposed to a rotating magnetic field which is rotating at 60 Hz, the voltages and currents induced in this winding are going to be 60 Hz. However, this is not the case about the rotor bars. The rotor itself is rotating at n of m, mechanical speed. So from the point of view of the rotor bars, the rotating magnetic field of the stator is not running at n of s, is running at n of s minus n of m, the difference between the two, the relative speed. And the frequency of the voltages and currents induced in the rotor structure are in fact going to be the same as the relative speed. So the frequency of the rotor is going to be S times f of E being the supply frequency 60 Hz. If the slip is 10% or 0.1, the frequency of the voltages and currents induced in the rotor structure are going to be 6 Hz, 0.1 times 60. And this kind of makes sense if you look at the boundary conditions too. Consider a rotor at standstill. At standstill, the rotor bars are going to see the rotating magnetic field of the stator rotating at 60 Hz. So the same frequency is going to be induced in them, 60 Hz. So the frequency of the rotor is going to be f of E. Does it match with this equation? Yes, because at standstill, S equals 1. So f of R becomes 1 times f of E. What about synchronous speed, the other extreme? At synchronous speed, both the rotor bars and the rotating magnetic field of the stator are going to be rotating at n of s, synchronous speed. Hence, there is no relative motion between them. If there is no relative motion, that means no voltage or current is going to be induced in the rotor structure. We show that with a frequency of 0. f of r equals 0. Does that match with the equation? Yes, because at synchronous speed, s is 0, slip is 0. So f of r is 0 times 60, which is 0. Now we come to the final activity. An induction machine turns at 580 RPM. How many poles does it have? Again, I would like to ask you to pause the video at this point, think about this question, and when you're ready, hit play. To solve this problem, you have to think about the equation for synchronous speed. N of s is 120 times f divided by p. So in a sense, synchronous speed is a multiple of frequency. Now the other observation that we had was the fact that mechanical speed is always smaller than synchronous speed. However, very close to it. Put these two observations together and you can make the following conclusion. The synchronous speed is the smallest multiple of frequency that is still larger than the mechanical speed. What is the smallest multiple of 60 that is still larger than 580? The answer would be 600. So the synchronous speed for this motor is going to be 600 RPM. And a motor with 600 RPM is going to have 12 poles.